we shall learn NMR of hydrogen nuclei, or otherwise we can call this as proton NMR. Nuclear magnetic resonance is concerned with the magnetic properties of certain nuclei. In this section, we are focusing on the magnetic behavior of hydrogen nuclei, hence the term proton NMR or hydrogen NMR. Hydrogen NMR spectroscopy is used more often than carbon NMR, that is carbon-13, partly because proton spectra are much easier to obtain than carbon spectra. The carbon isotope is only present in about 1% of carbon atoms, and that makes it difficult to detect. The hydrogen isotope is almost 99% abundant, which helps make it easier to observe. Another advantage is that proton NMR spectroscopy gives more information than carbon NMR. The word proton is used for hydrogen atom because it is the proton in the nucleus of the hydrogen isotope that is observed in these experiments. Although 2H deuterium and 3H tritium are also NMR active, they absorb at frequencies that are different from the ones used in hydrogen NMR. The proton isotope is also much more common than the other two. So proton NMR spectroscopy is more conveniently done than deuterium NMR spectroscopy. The most common form of NMR is based on the hydrogen nucleus. It can give information of any molecule containing hydrogen atom. Hydrogen nucleus, that is proton, has a nuclear magnetic spin. Proton absorbs different radio frequencies, or otherwise what we call this as chemical shift, compared to carbon-13 nuclei, and analyzes the chemical environment of hydrogen nuclei. Signals can have different number of peaks, otherwise what we call this as splitting. Proton nuclear magnetic resonance, proton NMR, is a spectroscopic technique that uses the magnetic properties of hydrogen nuclei, that is proton, to determine the structure of molecules, particularly organic compounds. It is a common and informative technique because hydrogen is abundant and easily detectable. Proton NMR spectroscopy is a type of nuclear magnetic resonance that focuses on the hydrogen atoms within a molecule working. Proton NMR spectroscopy analyzes the magnetic behavior of hydrogen atoms, that is protons, within a molecule when subjected to a strong external magnetic field. A strong magnetic field is applied, causing the hydrogen nuclei to align their magnetic moments. Radio frequency pulses are then used to disrupt this alignment, causing the hydrogen nuclei to absorb energy at specific frequencies. The absorbed energy is then measured, and the resulting spectrum provides information about the different types of hydrogen atoms present in the molecule. Hydrogen nuclei behave as little magnets, and a hydrogen nucleus can also be aligned with an external magnetic field or opposed to it. Again, the alignment where it is opposed to the field is less stable and at a higher energy. It is possible to make it flip from the more stable alignment to the less stable one by supplying exactly the right amount of energy. The energy needed to make this flip depends on the strength of the external magnetic field used, but it is usually in the range of energies found in radio waves at frequencies of about 60 to 100 MHz. It is possible to detect this interaction between the radio waves of just the right frequency and the proton as it flips from one orientation to the other as a peak on a graph. This flipping of the proton from one magnetic alignment to the other magnetic alignment by the radio waves is known as the resonance condition. And this is pictorially represented in this picture. So when the magnetic wave is applied, there will be a split. So spin up, this is nothing but plus half, will give you lower energy, which is unstable, and spin minus half, that represents as a higher energy, which is more stable. The transition between spin states give us NMR line when the magnetic field is exactly matches with the external radiation. So hydrogen has spin quantum number which is equal to 1 by 2. The possible orientation is nothing but plus half and minus half. The word proton is used for hydrogen atom because it is the proton in the nucleus of the hydrogen isotope that is observed in these experiments. Although deuterium and tritium are also NMR active, they absorb at frequencies that are different from the ones used in proton NMR. The proton isotope is much more common than the other two, so proton NMR spectroscopy is more conveniently done than deuterium spectroscopy. It reveals the following properties: chemical shifts. The position of a signal in the NMR spectrum, chemical shift, is related to the electronic environment of a hydrogen atom. Integration. The area under a signal is proportional to the number of hydrogen atoms in that environment. Splitting patterns. Interactions between neighboring hydrogen atoms can cause signals to split into multiplets, doublets, triplets, quadruplets, etc. Providing information about the number of neighboring hydrogen atoms. Proton NMR is widely used in chemistry and biochemistry to determine the structure of organic molecules, to identify different types of hydrogen atoms in a molecule, analyze mixtures of compounds, and study chemical reactions and dynamics. Proton NMR is common, abundant. Hydrogen is the most abundant isotope of hydrogen, making it relatively easy to detect in NMR experiments. That is, proton is the most abundant isotope of hydrogen, making it relatively easy to detect in NMR experiments. Sensitivity. Proton NMR is a highly sensitive technique, allowing for the detection of even small amounts of hydrogen atoms. Proton NMR provides a wealth of structural information. Applications. By studying the peaks of nuclear magnetic resonance spectra, chemists can determine the structure of many compounds. It can be a very selective technique, distinguishing among many atoms with a molecule or the collection of molecules of the same types, but which differ only in terms of their local chemical environment. NMR spectroscopy is used to ambiguously identify known novel compounds, as such the usually required by scientific journals for identifying confirmation of synthesized new compounds. NMR is primarily used for structural determination. However, it can also be used for purity determination, providing that the structure and molecular weight of the compound is known. This technique requires the use of an internal standard of known purity. So there's a mistake here. This technique requires the use of an internal standard of a known purity. Applications in medicine. Useful for identifying drug leads and determination of the conformation of compounds on enzymes, receptors, and other proteins. Best known applications of nuclear magnetic resonance to the general public is magnetic resonance imaging, MRI, for medical diagnosis, and magnetic resonance microscopy in research settings. MRI scanners use strong magnetic fields, electric fields, gradients, and also waves to generate images of the organs in the body. In most medical applications, protons, hydrogen atoms in tissues containing water molecules, create a signal that is processed to form an image of the body. Each subatomic particle, such as a proton, has a certain level of spin. By adjusting the magnetic field surrounding these subatomic particles, the spin rate is altered. As the spin returns to normal, the MRI machine is able to determine its location. Other applications. Another use for nuclear magnetic resonance is data acquisition in the petroleum industry for petroleum and natural gas exploration and recovery to study the molecular structure and interaction and determining 3D structure of proteins and other macromolecules. Moreover, in polymer production, it is applied in cosmetics and food manufacturing. MRI has now entered the arena of real-time process control and process optimization. Interpretation of proton NMR spectra. Number of signals indicates how many different kinds of protons are present. Position of signals, which indicates something about what we call this as chemical shift, magnetic or electronic environment of protons. Relative intensity of signals, which represents the proportional to number of protons present. Splitting of signals, that is spin-spin coupling, which indicates the number of nearby nuclei, usually protons. N+1 rules. The multiplicity of signal is calculated by using N+1 rule. This is one of the rules to predict the splitting of proton signals. This is considered by the nearby hydrogen nuclei. Therefore, N is nothing but the number of protons in nearby nuclei. Zero hydrogen atom as neighbor, which is nothing but N+1, which is equal to 0 plus 1, which is equal to 1, because this is singlet. One hydrogen atom as neighbor, so N+1, which is equal to 1 plus 1, which is equal to 2, it's called doublets. Two hydrogen atom as neighbor, N+1, which is equal to 2 plus 1, which is equal to 3, triplet. Other NMR types. While proton NMR is the most common, other NMR techniques exist that analyze different types of nuclei, such as carbon-13 NMR. Proton NMR spectroscopy is used more often than carbon NMR, partly because proton spectra are much easier to obtain than carbon spectra. The carbon-13 isotope is only present in about 1% of carbon atoms, and that makes it difficult to detect. Whereas the proton isotope is almost 99% abundant, which helps make it easier to observe. Another advantage is that proton NMR spectroscopy gives more information than carbon NMR. There's a comparison between proton NMR and carbon-13 NMR. Proton NMR on left hand side and carbon-13 on the right hand side. It is a study of spin exchanges of proton nuclei. It's a study of spin exchanges of carbon nuclei. Chemical shift range is 0 to 14 ppm. Chemical shift range is 0 to 240 ppm. Continuous wave method is used. Fourier transform technique is used. It's a slow process. It's a very fast process. Coupling constant range is 0 to 15 Hz. Coupling constant range is between 125 and 250 Hz. Peak overlapping seen in complex samples. No peak overlapping seen in spectrum. Solvent peak is not observed. Solvent peak is observed. Area under the peak is considered. Area under the peak is not considered. TMS peak is singlet, whereas TMS peak is quadlet. The effect of substituent on adjacent carbon atom can vary chemical shift. The effect of substitute on adjacent carbon atom cannot vary chemical shift. These are some features of proton NMR. Natural abundance of proton is 99%. Proton NMR is to determine type and number of hydrogen protons in the nuclei. The source of energy in NMR is radio waves, which have long wavelengths and thus low energy and frequency. The chemical shift range of proton NMR is 0 to 14 ppm. In a high resolution NMR spectrum, so this is NMR. So NMR spectrum, what looked like single peaks in the low resolution spectrum are split into cluster of peaks. The number of peaks tells us about the number of protons attached to the adjacent carbon atoms. So for example, you have number of adjacent atoms in the first column, number of peaks, second column, type of splitting on the third column, relative intensities of peaks are represented in the last column. So we have 0 adjacent proton. So number of peaks is nothing but 1. What we call this as singlet. The relative intensity is nothing but we have only 1 peak. So if it is 1, that is number of adjacent proton is 1, then we have number of peaks will be 2, and type of splitting will be doublet, and the relative intensity will be 1, 1. So if it is number of adjacent proton is 2, then number of peaks we observe as 3. Type of splitting is nothing but triplet, and the relative intensity of peaks will be 1 to 1. If the number of adjacent protons is 3, then we will have number of peaks as 4. Then this type of splitting is known as quadrat, and the relative intensity of the peaks will be 1, 3, 3, 1. Conclusion. The frequency of the observed electromagnetic radiation for a particular nucleus, such as proton or carbon-13, depends on the molecular environment of the nucleus, that is the electronic environment. This is why NMR is such a wonderful tool for structure determination. The signals of different protons and carbon atoms in the molecule show different signals, just like different functional groups show different signals in the IR spectrum.